Hi there, welcome back to my channel. How's it going? In the previous video we discussed the main axiom which lies in the ground of probabilities theory, and this video we're planning to explore the main theorems and fundamentals in probability theory. So the first theorem and the most basic one, it states that if we have two events A1 and A2 from the same sample space, which belongs to the same sample space, and conjunction A1 belongs to the A2, then the probability of event A1 is less than or equal to the probability of A2, and the probability of A2 minus A1 equals to the difference of probabilities A2 minus probability of A1. We can visualize this using Euler diagrams. So suppose we have the event A2 and we have the event A1, which belongs to the event A2. It's just a subset. So obviously the likelihood of the event A2 is much bigger than the event of A1. The second theorem states that for every event A from the sample space S, the probability of this event is less than or equal to 1 and greater than or equal to 0. So this probability of this event lies in between 0 and 1. For any event, let's say EJ belongs to S, its probability EJ is less than or equal to 1 and greater than or equal to 0. The next theorem states that the probability of an empty space, or in other words, the impossible event, equals to 0. Please note that converse is not true. It does not mean that if probability of an event EJ equals to 0, then EJ is impossible event. This is not true. We already discussed this in our previous video. Please get back to our previous video if you don't remember this part. If the probability of our event is equal to 0, it does not mean it is the impossible event. This is really fascinating stuff about probabilities theory. Let's go next. And if A prime is the complement of the A, then the probability of A prime equals 1 minus the probability of A. That's it. If we have some kind of sample space S and we have the A, then complement of that is the space which goes beyond the space of A. So this is everything except A. So this is everything except A itself. The next theorem is that if we have A which equals A1 union A2 union A3, A4 and so on until the AN. In this case, the probability of A equals to probability A1 plus probability of A2 and so on until the probability of AN in case they are mutually exclusive. We already covered what mutually exclusive is, so please refer to our previous videos where we were discussing this. These ones are mutually exclusive sets. This can also be written as the sum of AI, where I takes on values from 1 until the n. And sometimes we also denote the A as the union symbol, which I takes from 1 until the n itself, like this. This is just a different notation. Alright, let's go next. Let's suppose we have two events, and they may not be mutually exclusive. We're not sure if they are mutually exclusive or not. We have event A and event B, then the union of event A and event B, and the probability of this union equals to the probability of A plus the probability of B minus the probability of A and intersection of B, and it is easily can be shown using the Euler diagram. Suppose we have two circles here, A and the B, and we can see that the union of these two sets and the area of union these two sets will be equal to A part plus B part plus B part without its intersection, just because it doubles here. When we sum up their probabilities, we count this value twice. The first one which is included in P of A and the second one which is included in P of B. That's why we need to subtract one of its intersection, A intersection B, which equals P A union B. We have two more important theorems here. The probability of P of A equals to the probability of A intersection B plus probability of A intersection B prime, where B prime is the complement of B. We can also show this using the Euler diagrams. Suppose we have A and suppose we have B, then the intersection of this plus the intersection of A, this is the intersection of A, will give us the actual probability of A. But we have to keep in mind that this part is essentially the intersection of A with all the outer part of the space which goes beyond of the set B. Where is this A? Where this is the A and this is the B. Alright, so the next theorem that states that our P of A equals P of A intersection A1 plus P of A, A2, and so on until the P of A intersection AN, where the events A1, A2, A3 until the AN are mutually exclusive, and any occurrence of the event A must result in the occurrence of one of the events from this set, from A1 until the AN. So if our A1 occurred, That means one of the events aj occurred, where j is the number from the set from 1 until the n, and aj are mutually exclusive. Mathematically, it is also can be written as the summation of a intersection aj. J takes on values from 1 until the n, and it can also be shown as Euler diagrams. Suppose we have some kind of a, which results in some of the events a1, a2, a3, which are mutually exclusive. We have lots of these events. They make up the whole a, essentially. And at the same time, they're mutually exclusive. They do not intersect. A1, A2, A3, and so on. So that's about it for today's video, and I hope you found this video helpful. If you have any questions, please leave them in the comment section below. We also have our Discord community. Feel free to join us in our Discord community. You can find the link in the description. And as always, see you in the next episode. Take care.